typically when we look at something going through some kind of nuclear change, like alpha decay or beta decay, we think of it as going from less stable, less radioactive, to more stable. That doesn't necessarily mean that one nuclear change is enough to fully stabilize a radioactive isotope. Well, in a lot of cases with very big unstable atoms, like this thorium-232, we have to go through quite a few changes in order to get something to be fully stable. And that's what we're going to kind of look at for this assignment here. Okay, so we're going to look at what's called a radioactive decay chain, where we end up emitting radiation multiple times and continually change the isotope until it becomes stable and stops changing. Okay, so this usually includes quite a few steps, especially again for these bigger isotopes. So this example is plutonium, all right, specifically plutonium-241. Okay, so the first nuclear change it goes through is a beta decay, and then it goes through an alpha decay, and then an alpha decay, and then a beta decay, and it keeps on going and going until it reaches an isotope that is no longer radioactive. Now, in these cases, since we're going to be showing a whole bunch of nuclear changes kind of one after another, we can kind of simplify this a little bit by not showing the full process. If we wanted to make sure all the mass and energy is conserved in these processes, we would write a nuclear equation where I would have something like this: plutonium-241 in an arrow, and on the right side I would show what it changes into plus whatever particle I'm kicking out, like a beta particle from beta decay or an alpha particle from alpha decay. But in this case, since I'm not going to be changing what happens to the beta particle or the alpha particle after it leaves, it's just kind of gone, we can kind of ignore it and say, yeah, as long as I know what happens to the original isotope and keep with that, I should be okay. So to keep that simpler, whenever something goes through alpha decay, remember that our mass number drops by 4 and our atomic number drops by 2. That's because an alpha particle is a bundle of 2 protons and 2 neutrons. So that thing that we kick out has a mass number of 4 from the 2 protons and 2 neutrons, and an atomic number of 2 from having 2 protons. Okay, it's a helium nucleus essentially. Okay? If something goes through beta decay, the mass number stays the same because we switch out a neutron for a proton and an electron. The electron zips away as a high-speed electron that cannot be contained in the nucleus, but the proton stays. So mass number doesn't change, but we now have one more proton than we had before, so that atomic number goes up by 1. So rather than trying to write out the whole nuclear change for each one of these steps in the nuclear decay chain, the radioactive decay chain, we're just going to look at how our mass number and atomic number changes after each step. So like, for instance, for our plutonium here, let me get a pen. Let me change my color here. All right, our first beta decay does nothing to the mass number, but our atomic number goes up by 1. Beta decay increases the atomic number of 1 because we switch out a neutron for a proton and an electron. The electron escapes. Okay, so 94 plus 1 leaves us with an atomic number of 95. 241, our mass number, stays the same. So it's just going to continue being 241. Okay, this resulting isotope, americium-241, with an atomic number of 95, goes through another change. So, for instance, we go to alpha decay next. So if this is going through alpha decay, its mass number is going to drop by 4, and its atomic number is going to drop by 2. So what we're left with is 241 minus 4, that's 237, and 95 minus 2, which is 93. If we go look up 93 on the periodic table, atomic number 93 is neptunium. So we have our next isotope figured out too. And then we keep going from there. We go through another alpha decay, so minus 4 on our mass number, minus 2 on our atomic number. We're left with protactinium-233 with an atomic number of 91, which then goes through a beta decay, so our mass number stays the same. We add 1 to our atomic number, and we go on and on and on. Okay, so we're going to look at a radioactive decay chain, again for this thorium isotope. All right. It's going to be 10 steps, and after each step where this thorium-232 changes, we're going to get an answer. So our questions for this assignment are basically going to be, what is this guy? What is this guy? What is this guy? What does our isotope turn into after each decay? Okay, and again, we can keep this simple just by looking at what decay happens and adjusting the mass number after each one. So if I take my mass number of 232 to start with, and this goes through alpha decay, that means that my mass number drops by 4 and my atomic number drops by 2. Okay, it's kind of a bad 2, but you get the idea. Okay, so my new mass number is going to be 232 minus 4, which is 228. All right, and my new atomic number is going to be 90 minus 2, which is 88. Okay, so this is some isotope with a mass number of 228 and atomic number of 88. I could go and look up what isotope that is. Okay, what element that is by looking up the number 88. Okay, so I find out what element that is, and I can call it that specific name. The next step, I go through a beta decay, where my mass number stays the same, so it's going to stay at 228. Okay, but my atomic number is going to go up by 1. So my new element is going to have an atomic number of 89 instead. So I would have to go look up what has an atomic number of 89, and that would be my element for number 2, with a mass number of 228 and an atomic number of 89. And then we keep going and going and going. Mass number stays the same for beta decay. Add 1 to the atomic number. What do we get next? We go through an alpha decay. We drop our mass number by 4. Our atomic number drops by 2. What do we end up with here? Okay, now if you have a mistake early on, okay, that means that the rest of your answers after this are going to be messed up. So if you try this the first time and get a terrible score, like a 2 out of 10 or something like that, don't freak out. Go back and see where your mistake started, and then rework the problem from there. Just be careful about how you adjust your mass numbers and atomic numbers. There are multiple tries on this for a reason. Okay, so there isn't a whole lot new to this. It's just the alpha decay and beta decay we've seen before. We're just doing them multiple times in a row to the same isotope instead of seeing them in different separate problems with separate isotopes.